What's happening? We got rainbows. We got everything. It is time to go. How you doing, Brad? What questions are there? Yeah, I love that. You sat down. I got my coffee. I need the second cup of coffee today. We got this. It is time. Let's do this. What questions are there? Which one? Yeah, it's kind of like a downhill thing. As you do more and more of this, it kind of just gets easier and easier. I know that sounds obvious, like, oh yeah, of course, the more you do it, the easier it gets. But it really is. It really is like one of those things you just keep doing the work and you're like, oh, it's getting easier. It's like, oh, this is kind of the same thing. We're just building models here. We're just seeing different models, building different models, make the model, explain the data. Let's see here. Do I have the assignment open for you guys? Do I have there's someone there? Which one's this? This is the one right here. Homework 8, the big one. So question 2A. There's question 2A. This is the one where we build it without the offending row. And is this the one right here? Am I doing the right one? So we should go to data, ex4 bike. We don't have that because we need library reg class. Always work on your assignments early. Make sure you can knit because sometimes you can't knit. And there's the model. So here's our model, and replace the offending row number so we make it without it, and we can get a summary of it. And the big thing we're looking at right here is we compare models. Was everything trying to close? There's where my brain just, why is it giving the, sure, it's from earlier class. The way it works is with the different models right here, we're seeing that if you compare models, we did this yesterday, we made like the old model. So we found the offending row, and this is dealing with leverage and influential points, so that's not the old one. You can do this. This will make the old model. It's just using all rows and all columns. And we're just going to take this, put it here, and do this, and go to m.old. And here's the old model. And we were able to figure out, you can get the RMSE from this. You can get like a few different ways. We figured out, Ben figured out a way in class. If you notice, the RMSE here is 1365. So if you want to get the RMSE, you could probably go to ANOVA m.old. So feel free to ask questions. Could not find ANOVA. Oh, because it's lowercase. And we want this right here. Which, does this save a table? Let's go mold. Save into it for the moment. I'm just having some fun. Use, yeah, you can do, oh, we'll do the sigma? Really? Is that just it? Well, all be. We're going to do it like a harder way. Yeah, because it's, and you can probably figure out, because if you go right here and you call this like m.old sum or something like this, you can store it into here and you'll actually get the complete options now. We want m.old sum, and now you'll do, is it sigma? There's sigma. So you can then use this sort of notation here to use it on that. So you can, once you figure out how to reach inside of here, it's weird that it doesn't give you it until it's stored, I guess, because the object's not created. So you could get the old and the new, and you could compare, and we kind of want to look at the reduction in these. So there's your reduction right there. We can also look at the R squareds and look at their reductions. And you can tell I had some coffee here. Adjusted. It's not adjusted? What? What are you doing? Oh, it's got the, no? Oh, I know why. We got to do the m.old sum $. It's acting weird again. Can I get some help with question 5? Yeah, you bet. Of course. Hey, what's up, Carly and Caroline? We're just having some fun with this data right here. I'll finish this up with Brad right here. I'm going to do this. I'm going to store this into, oh, did we just call this m.old? And then, oh, I think I know why. It is, okay. So when I had that, there we go. So if you have the $, it creates all these issues, and I've noticed that before. So for all this, and here's adjusted R squared. So you could do the same sort of code we have right here and grab and change this to the adjusted R squared. And you could talk about versus your old and your new. And this one we want to get higher. So actually we might say our new R squared is this much higher than our R squared adjusted, that is. Does this make sense here, Brad, what I'm doing when I compare? These are the important lines of codes. One 111 and 112. So the biggest thing we want to look at, Brad, is the R-squared adjusted, because R-squared adjusted is going to be a much fairer assessment, because when you talk about your output, if you're like looking at your old model right here, you've got R-squared, and yeah, you want R-squared to go up, but R-squared adjusted is going to be a fairer assessment. And R-squared assessment is, the R-squared adjusted is 39%, or 39.47, and the new one right here has an R-squared adjusted of 41.6, and I can look at that and I can get the differences between them, which is like 2%. So the R-squared adjusted went up by like 2%, which is because it's a multiple model. Does that make sense, Brad? In the multiple world, R-squared adjusted is a much fairer assessment. Does that all make sense? Like, so I'm just comparing my new one compared to my old one, and I want to say like the new one is 2% higher than the other one. Yeah, the code's showing the difference. It's just the new R-squared adjusted compared to the old one, and then this is the old sigma minus the new sigma. And the sigma right here is the RMSE, even though I wish it just said RMSE. I just ran the summary of each and got, yeah, you can do that. It's perfectly fine to do that too. I'll drop this in the chat. You want to see something really cool, Brad? Do you want to see something that'll blow your mind? Watch this. Let's call this, and then I'll hop over to the other question right here. Let's call this diff 1. And let's call this diff 2. So watch this. You ready? I'm going to go down here, and I'm going to say response. And for my response, we'll put in, so I'm going to go response, and that'll be bolded. And I'm going to say, we notice that the difference in RMSE was, and then I'm going to do the following backtick, R diff 1 backtick. And that should be, yep, it's a different color if you notice it. It's really hard to see, but that's a slightly different color right there. Also, the difference in R-squared adjusteds. Ooh, if we want to get really fancy, I won't do that because I'm wondering if it would work. You can do dollar signs here, and you can do like R, and then then we do this, R-squared. There we go. Adjusted was, and then let's go right here, backtick, R, and then diff 2, period. Okay. This should knit. I don't know why it wouldn't knit. Let's see if it knits. Let's hope it knits. It's going to knit. It's knitting. And now when we knit this in here right here, what do we see? Oh, it's doing it really big. Oh, that's our square adjusted of that. Where do we have it? Here we go. Look at this. Oh, it did the dollar signs. Wait. Do I have to do double dollar sign for me to do it? I don't do LaTeX writing as much. Let's try one last time on this. And yeah, so it'll insert it in there for you. See, it's doing this right here. So I'm just going to write R square adjusted. I don't want it to look like that. I've had a problem with LaTeX writing on this. So you can literally make it so it inputs it in. So if you're writing, it's really a good habit, and I'm going to probably start trying to teach people how to do this, because here we go right here. You could round it and stuff. We noticed that the difference in RMSE was 26.21. Also, the difference in R squared adjusted was this. And so it literally just solves it for you. You don't have to worry about misentering it. If you solve the code correctly, if you change what you're doing, it'll change. So just so you can see the code in the background, you have to then put it in here, and you're calling an R chunk. You're calling an object in the R environment. So what this does is it reaches into the R environment and puts this value right here. So I think it's a really cool thing to do. I've done it in some reports that I've written. You don't got to guess about it. You just got to be like, oh, let's just store that object, and then let's call that object. And then if you write, like if your report changes like weekly, you could just do, every week you could update the report. So there it is. And if you wanted, you could just go to like, what we should do is we should do like round. Let me think. That's the difference in RMSEs. So yeah, so that should be that. I think, ooh, that's probably not going to like it. Yeah, I'd round it. I'd do whatever. It's, yeah. Okay, we're good. Yeah, you can't round it like that. You can't store into the round. You store 2 seconds. Round 2. And this one I'd round to 4 digits. And last check. And then let's hop over to some 474. How's that look? There we go. There it is. It's all fixed up nice and neat. And so it's rounded for you. It's all done nice and neat. Don't got to worry about formatting. We just store that. If you want to be super fancy, you could remove this output. So yeah, you can like not make the output show, but yeah, it's kind of just good writing reports. Let's hop over to predictive analytics for some 474. Can you go over number 5 and 9 on 474? Number 5 and 9. We did 8 in office hours today. So let's go over to 5. Where's 5 at? 5. There it is. Wait, am I going mad? What does 5 start with? Is there not, did we change the numbering that there's no like number 5? It just like skips. What is the start of number 5? What does your number 5 say? Oh, wait, I think I see it. Here it is. Here it is. Okay. Is this the interpretation? Yep. Consider the value data. See, I guess, I don't know why that's not a chunk. We could make it a chunk. See, wait, where is this at? That's a bummer. It says 5 and then just not in the chunk. Oh, and it says Q4 below that. That's maybe why. Consider the value data using the LM function, not trained from the caret, fit a multiple regression model predicting this from here. Using all predictors, no interactions on the entire data set, print to the screen a summary of the fitted model, interpret the coefficients. So we're going to put this right here just so we can kind of see what's going on and consider the value data set. So this is probably in reg class. Let's go ahead and take a look. And the way to know what data set it's in is you go to value. What? It might have loaded up with the original environment. Let's get the value up. We got some stuff on the screen. That's good. Why do I not have the value data set? Consider the value data. Let me load the environment. Did that load? Didn't load. I know why. Sessions, set working directory, choose working directory. Sorry, every time I load up. And it's BAS 474. Session, let me go to here. And where did I load it today? Homework, predictive analytics 2. I think it's this one. And now, there it is. Got it. Okay. Running your code, I keep getting chunk pending execution. Send me it. It might be, you might have plots that are showing up, Megan. It might be your plots that you're trying to display plots. Send me a screenshot of it. Send me a screenshot of it. And I will take a look. So good question. My guess is that down here, like, do you have a line of code that you were just, I'm guessing that you ran a chunk and then it's still running code. And go to your here's my suggestion. Go to the bottom console and see if it's asking you for input down here. Like, go down here to the bottom. And if it's saying like hit enter to continue or something like that, you might see this on the bottom screen. And you can hit like escape. So you just want to hit like escape down here. Been saying it since the last assignment. Oh no, send me an email on that. But go to the bottom console. And I'm guessing you have something like still executing code. And go to the bottom console. Yeah, and then click down here and just go escape a few times. That usually clears everything up. But good question, Megan. Thank you so much. 100 office hours bonus points. Let's go here. Now that we got the data, predicting customer LV, tilde dot, with no interactions, print to the screen the summary, data equals value. And so let's do the summary of it. And summary of model, and here we are. So we've got a ton of stuff going on right here, and this is actually super important. If you're 320, listen up, because these are things we should be able to do. So when it comes to interpreting coefficients, we have to know what kind of coefficient we're dealing with. So the interpretations of these coefficients depend on what type of coefficient it is. When we look at total transactions, is that going to be a quantitative or a categorical variable? We're predicting the lifetime value of a customer, which is quantitative. Is the amount of transactions they have quantitative or categorical? Is the amount of transactions they have quantitative or categorical? The amount of transactions they have. Would that be quantitative or categorical? The amount of transactions. That's the key question, which 320, this is big for you guys too. It's quantitative, yep. So what we need to do here is we need to talk about what's mathematically going on right here. The really bad interpretations, and I need to say to my grader, just destroy the points if this happens. Sorry, that happens to you. But you don't want to say like, if you increase your total transactions, then your customer lifetime value goes up by this. We want to say two customers who differ in their total transactions by 1 are expected, and where's total transactions? It's right here. The coefficient is right here. So two customers that differ in their total transactions by 1 are expected to differ in their, oh, you're welcome. Two customers that differ in their total transactions by 1 are expected to differ in their lifetime value by 165.9598, where the customer with a higher, amount of transactions is expected to have a higher lifetime value. So we're just literally saying like two people who have this difference are expected to differ by this much. Do not use words like will. 320 will tell you, Brad's in here. Don't use that will word. It's very, very bad. And there's notes on how to interpret this in the slides. And I've done it like 1,000 times in class, and I realized like you just have to go and like take a look at it You're so welcome, Megan. Glad that's working out. That's what we do. We get it working. Come to office hours. We get the code working. I was thinking about it and I was like, I need a picture of it. And I was like, no, I think I know what that error is coming from. It's you probably executed something that did like extra equals true or many equals true, and that'll have you prompt for more things at the bottom. So it's just being like, I need to have more inputs. So who's good on the total transactions? We good on this one. Make sure you have a very thorough interpretation. There is interpretations in the notes, and make sure you see how it's two customers that differ in their total transactions by one. But we should say but are otherwise identical. Very sorry, please include that. Two customers who differ in their total transactions by one, but are otherwise identical, are expected to differ in their lifetime value by 165.95, where the customer with more total transactions is expected to have a higher lifetime value. It's a lot to say. It's just generally speaking, we see people with more total transactions, all else equal, the people with more transactions have more lifetime value, are predicted to be higher. Not that they will, but are predicted. Does that kind of make sense right there? Like there's a positive relationship between this, that the people who have more total transactions are generally going to be expected to have higher lifetime values. Everything else equal, because we're not considering the other variables here. We're just talking about how this one variable impacts customer lifetime value. So hopefully that makes sense on the interpretation, how we're not saying it'll cause a higher lifetime value, but what we would expect given two customers differ. Now this one clues you in on this right here. We've got gender male and gender female, and female is the reference level. More on this tomorrow for 320. So when you compare right here, you've got two customers where one customer is male and the other customer is female. The customer who is male is expected to be this much higher in their lifetime value than female. That's because we're doing the comparison here between male and female, and this is the interpretation of the indicator variable. 320 will be going over this very in-depth tomorrow. So if you do want to practice this tomorrow, 320 is having a very in-depth lecture on this. Since this is kind of talked about in 320 and the notes for 474, we kind of go through it a little quickly, or we have it like in the notes for you to reference. And this is more of a descriptive analytics thing, so we don't focus on it as much. We still want you to know how to do some descriptive analytics, but if you can't tell, the whole focus for a while now has been predictive analytics. So we've been really focusing on making predictions and using the carrot package. But this is just classical descriptive analytics. This one right here, it clues you in on here. The reference level is an income level between 0 to 30,000 that is. So two customers where one customer, two customers who are otherwise identical, where one customer has an income level between 30 to 45,000 and the other customer has an income level between 0 to 30,000, they are expected to differ in their lifetime value. And you could just say the positive value. It's debatable, but you will say the customer with the $30,000 to $45,000 income is expected to have a lower lifetime value. You could say by that amount. We would expect them to. Does that make sense? It was Caroline. Is this making sense, Caroline, how to interpret these? Make sure you say the but are otherwise identical, because these are multiple regressions. Sorry, just taking that last sip of coffee right there and making sure it needs to be but are otherwise identical because it's multiple regression. In multiple regression, we have to pay respect to the other variables and say, so income is categorical. Yep, income level is categorical because these are all indicator variables. And so you see these are just different groups right here. We can confirm this by going to the value data frame. And well, one, you could do this. You could go class value and then $ income. And it's a factor, which means it's categorical. And you could also get a summary of it, and we can see that it has different levels to it. So making sure you check things like this, like really good questions right there. So it's categorical. So we compare the indicator level to the reference. So it's not for each one unit. Well, we don't even use that, but not for two customers who differ by 1 unit in their income level. It's two customers who are otherwise identical, where one customer is in the $30,000 to $45,000 income level and the other customer is in the 0 to 30,000 income level. We would expect them to differ in their total lifetime value, customer lifetime value, by negative 22.5156, where the customer that's in the 30 to 45,000 group, we would expect them to have a lower lifetime value. How's that sound, Caroline? Does it make sense? Do you mean to slow it down or anything, or like last little bit of coffee right there? I think hopefully those interpretations make sense. Got it. Good. And I think Madeline, was it Caroline? Another one? There was another question, number 9, I think. Number 9. It was so crazy during class today. My brain just fried itself. I was like, I know how to do AUC ROC. And I was like, oh my gosh, I can't draw the picture today. Was it number 6? Can I get help? Number 5 and 9. 9. Let's hop down to 9. We did 8 in office hours today. Oh, cool. I love this one. Oh, this we got this. We got this. We can crush this. We haven't talked about this in a while, though, so this is a really good review right here. So we've got some really good stuff right here. 6 and 9, you bet we'll do 6 next. So 3 models are being considered. The estimated generalization errors of each have been found with cross-validation. Cool. So these are the validation portion. When answering the following questions, find and report the number of standard deviations that separate the 2 models' errors. Remember to use the larger of the 2 standard deviations. Okay. So we've got model A, model B, model B, model C. Okay, cool. So according to the 1 standard deviation rule, is there a preference between B and C? Okay, so let's compare B and C. So what's the 1 standard deviation rule? Models what? That are within what? Are what? Models that within what of each other are what? What's the 1 standard deviation rule? It's basically what it is. What does it mean for those models? Models that are within what are considered what to each other? How can we look at the predictive power of a model? Basically identical. Yep. Great job, Caroline. 100 office-hour points. Models that are within 1 standard deviation of each other in their performance, like on the RMSE, are basically identical because the RMSE is just an estimate. And so when we compare these 2 models right here, what are we going to do between their 2 standard errors? When we take the 2 standard errors, we're just going to find the what of the 2 standard errors, which these are residual standard RMSEs. These are RMSEs. What are we going to do to the 2 RMSEs? We're going to take them, and we're going to do what to them? I'm going to take them. Oh, I already did it. Well, we're going to take them, we're going to subtract them, and then we're going to divide by the what of the 2 standard deviations. We're going to divide which of these 2 standard deviations will we divide by and why? Kind of says it up here. We will divide by the what are standard deviation. We'll take the difference between the 2 models and how they perform, and then we'll divide by the whicher of the 2 standard deviations. The bigger. Carly, nice job. 100 office-hour points. Yep, grab the bigger one, drop it down here. And that is the difference between model B and model C, as long as I haven't mistyped something. So you could go here and put a hashtag and say difference between B and C. Are B and C different models in their predictive abilities? Are B and C at all really different? Are B and C different? They're within 1 standard deviation. The answer is most definitely yes or no. Are they any different, like in terms of real differences? Are B and C really that different in predictive power? Yes or no? Are they really? No, they're not that different at all. They're really not that different. We could do another model here. We could just grab this one, and this is the difference between A and C. And I do have them reversed right there. Don't worry, it's just the difference. And you can see A and C do have a clear difference. And you might say, why am I using 3.5? I'm using 3.5 to compare the models because 3.5 is the bigger of the 2 standard deviations. So we're comparing this value right here versus this value there. And then we're going to take the bigger, wait, 3.2, sorry. Because the standard deviation of 3.2 is for this model, and the standard deviation of 2.2 is for this model. Gotta be careful, that was an error. So we're going to use the standard deviations that's the bigger for the 2 models. So this is almost all the comparison metrics we could do. The only other comparison we could do is between A and B. So between A and B, the bigger of the 2 standard deviations is the 3.5, and then we would compare 29.1. And so we do see a difference there. So this one here has no difference. Like they're basically like no real difference. Difference. And this one down below has a difference too. How am I doing this? I'm just standardizing their difference to see how many z-scores it's away. That one's less than 1 z-score. So point is difference in standard deviations. It's, yes, how many standard deviations the model's predictive powers are apart. The models have a difference in their predictive power that is 0.8 standard deviations away. So the difference is very minimum because since we're standardizing the difference, think what standard deviations mean. It's like a standardized unit of distance these models are apart. They're not that far apart. Does that make sense, Caroline? So when we say they're 0.8 difference in standard deviations in their predictive power, we're not talking about this difference right here, because that's a difference of 2.8, I believe. That's a difference of 2.8. But we're talking about in terms of standard deviations, it's only 0.8 because there's really not that much difference once we standardize it. So we do not have that big of a difference. How does that all sound? Hopefully that all makes sense right there. think we might be good. Got it. Good job. Let's look. What was it? Number 6. Number 6. What happened to the numbers? Can you do? Yeah, I'll do that. You got it. If 320 appears. 6. Where are you? Question 6. There we go. In nearly every sample we do, we split into training and holdout samples. With the sample command so that which rows, this 2 sets are picked at random, we can't just specify, say, let's fit the first one. Oh, yeah. Come up with an example where this would be a bad idea. Yeah. Hint, whatever splitting method we use is fine as long as there is no systematic differences in the characteristics of individuals in the holdout sample and the training. Yeah. I mean, that's so true. I don't want to give this one away completely, but the idea of the holdout is completely random. Does that make sense? Like the holdout is a random subset of our data. So the point of the holdout is to have randomly selected individuals or with the response to put in the value or knit, but because the homework states to put the code after the response, they won't knit. Oh no, maybe send it to me, Brad, and I'll take a look. Oh, just run your code like before or something. Maybe that'll fix it. But if you want to send it to me, I'll take a look and fix it up. But when would this cause problems right here? Because I've seen people do this. People do this for like their 201 data sets. They'll go and they'll just take the first, like, we'll be like, take a sample of 500 rows, and they'll take like the first 500. And that's like one of the worst things you could do ever when we say like, take a random sample. And then so let's open up data survey 10. I don't know if this one has any structure to it. And that's kind of the answer. Yeah, don't worry. If they take all points, just tell me. Just be like, hey, Brian, they take all points. I'll be like, yeah, they shouldn't. That's always my response. I'm pretty nice on points, but I mean, like, if you do something if it's a structural thing, I don't care. If it's like a response thing, then there should be points off. So yeah, I think it's cooler to learn new things and be like, oh, I can get it to do this. I can write my report like this. This one does not look to have a structure to it. But what am I getting at? That if there's a structure to the data, imagine this. We go and we do a survey of UT students, and we go and we speak to, in the morning, we go and we speak to people on main campus. And then in the evening, we go down to the ag campus and we speak to people at the vet school. And then someone says, let's split our data up into 80% training and 20% holdout. And we'll take the end of the data. Can you see the problem? Who can see the problem? Let's listen to the problem again right here and see if someone's like, well, let's just cut the data. First 80% is training and the last 20% is holdout. So we start off in the morning on the main campus, and then in the evening we go down to the ag campus and we collect data on people on the ag campus, like at the vet school and all that good stuff. What would be the issue right here? What would be the issue? When they say, oh, let's just take the first 80% and make it the training. No ideas? Dun, dun, dun. It kind of, so it's not the equal splitting part's not that big of a deal. I think you're getting at it, Carl. I think you're getting at it. It's that I think what you're saying is the people on the main and the ag campus would not be equally split out and randomly put into the training and holdout. There would be, what you want when you make your training and your holdout is that the training and the holdout look like each other. Like you can't have the same people in the holdout that you have in the train, because you have to make your model on some data and then test it on another set of data. And that's, you make your model on the train, you test it on the holdout. And so we randomly, as Vadran is putting 100 points, Vadran right there, as we randomly put people into the holdout, it would be likely that we'd have an equal percentage of on-campus students or main campus students and ag students in both of them. We'd have an equal percentage, it would seem. Not like purely equal, but any differences would just be due to, random chance. So any differences we really see between them would just be due to random chance. But if we take the first 80%, then we would see if there's some sort of time order relationship to the data, where we collected people from the main campus, then we went to the ag campus, we would see a lot more people collected from the, Does that make sense to everybody? That's what this question's getting at. It's why we do random sampling. So I feel like my volume's been a little bit lower lately. One of these days I'm gonna like look into it. Isn't there like a master volume for it? Go mixer. There's the mic. The mic's at 97. Now it's at 100%. Do this. Oh, yeah, it does do it. That's so weird. Why doesn't... I don't know. I've got this all the way over here. There we go. All that fun stuff. All that fun stuff. So let's look. There was another one. 2D. 2D. What's 2D say? This one we did earlier. And so are you talking about this one right here? Carly, you're talking about this one right here. We did this whole problem. I'm trying to think. To do this whole problem, you have to do every other part of it. Just response. Okay, cool. Yeah, because we did. So what's the response I want you to talk about? Okay, good. And it's, if anyone's watching this right now, it's in the video from Monday. I believe this is in Monday's video. So go watch Monday's video. We go through all the code and check it out. Monday's video. You'll see me coding this. We'll code the for loop. We went through it. So great job. Good job on getting this one. It's pretty tough. And so, I mean, we can do it if we want, but what's the response want us to talk about here? Okay, what's the response ask? Oh, whoa. I'm sorry. Is that good or bad? Maybe you want a small part. But you're like, yes, I saw it. It's so tiny. Yes. That's, or maybe, no, Andrew, I'm sorry. You'll likely need an if statement for looping. What is their response want us to talk about here? The results matrix, yada, yada, yada. Using nested for loop, you receive numerous warnings, of course, because ranked deficient because of the ones we're missing things on. Produce the two sanity checks and determine which model happens to do the best on the holdout sample. Now, here's the thing. To determine which one does the best, which looks to be the response, you'll need an if statement. Yep, we got that right there. We did that. Okay, so the response would be which one does efficiency is just cheap and easy. Yeah, exactly. So when you have this matrix right here, which probably can't store that as a matrix. Cracking me up, Andrew. You want to do which, and you want to go to your matrix, and we can kind of test this out right now because we can make a matrix right here. So we're going to store M into matrix just for the, don't do this. I'm just having fun. I think if we do this, let's take a look at it. Cool. So if you see the minimum, we're going to put the minimum right here. And let's do the following. Now it's there. And 3 by 3, that's 9. So cool. Okay. And this is just an example matrix. You'll see why we're doing this here in a second. So which matrix equals min of matrix. Now what this will produce, it won't produce, let's say it's right here, 1,000 points. Who knows what answer this will produce? What answer will this produce the way it is right now? What answer will this code produce right now? What answer will this code produce as written? 1,000 points, who knows? So which returns positions? Which returns... Here's a hint. I'm going to give 1,000 points for everyone who guess. Phaedrina and Caroline, 1,000 points for taking a guess at it. The answer is this will return 5 right now as is. This should return 5. Oh, it returns, oh, because I can't spell. Ha ha ha. And the answer is the code does not run. Oh, because I didn't call it matrix. I called it M. Okay. This will return 5. There we go. Now it returns 5. Sorry. So why does it return 5 is the question. It's because of the way the code works. And we can show this by doing the following. Now it'll return 4. Okay, so what is this code doing? The code as written right now is going through the matrix and finding the minimum value. But the way the code searches through the matrix is it goes downward through the columns in an orderly fashion. Do you see if you go 1, 2, 3, and that would be the 4th position right here. Previously 0 was the smallest. So this is doing it by just like positions by going down each column as a vector and then restarting the ordering by going to the next column. We don't want that though. There's a much better way where if we just go to array index, there we go, equals true. And now we will get 1, 2. And so you're going to get, when you do this as your result, you'll get 2 results. You'll get, the reason being is because you have a symmetric matrix. We'll kind of parity this right now. So you'll get this kind of result right here. because in your matrix, with it being completely symmetric, which this one is not, we could make it more symmetric, you'll have the minimum value in the same spot as it is. And it's just like the same combination of like x5, x10, x10, x5. Does that make sense? What's going on with this problem is you're making a combination of all of the, I guess technically you could have like x3 be the best, and then you would get the diagonal. If the answer is the diagonal, which I'm pretty sure it's not, you would have only one answer because these models here just have one variable. Like this is the x1 model, this is the x2, this is the x3. This is the, right here, these models would be the x1, x2 model, and this is the x2, x1 model. So it's still the same values, and so this matrix should be symmetric. We could kind of parity it a little bit better here by going 3, and then this 4 should be 8, I believe. Yeah, and now the way this looks, it's still the same, but this is more what your matrix will look like. So your matrix will have a diagonal of the single variable models, and then your matrix will have the RMSEs. Yeah, so the minimum, because we're trying to minimize the RMSE, so you'll probably get values closer to this. It's RMSE, right? I'm pretty sure we're calculating RMSE. Yeah, it's like boot RMSE. Or no, this is not boot RMSE. RMSE. Yeah, if we're doing RMSE, it's got to be minimum, because RMSE is typical miss the model makes, so we want to minimize that. So the goal is to look through here and see which combinations of variables return the minimum RMSE. Does that make sense, Caroline? So unless it was R squared, because if it was R squared, then we would want the highest, and we might be looking at adjusted R squared. But since we're storing the RMSE here, we want the minimum RMSE. So you'll use a code like this. Here, I'll drop it in the chat. So that kind of code right there, we'll run it and find the position. And it'll look like this. Your matrix should look like this. Is just like a smaller version, but it'll find the position of the minimum values in the matrix. That's some good stuff right there. What else is there? Does that make sense, Caroline, everybody? Some good stuff right there. All the good stuff. We were doing tweets earlier. We had the Delta data set. It's such a fun data set. I found it. You can go to tweets. You can look up the tweets that people said. There's, oh, it's text, isn't it? It's text. Here's a bunch of tweets. I don't know what these tweets are going to say, though. Then you can search the tweets. You can go to grep, and they do the pattern first, right? I always forget grep's order. Hello! And these are the positions where people said hello. So then you go here, and you go to tweet, $text, and you return the position. And then you can see what people have said. You can go to worst ever. 12 calls in the span of 2 days, none of which available to speak to someone. Oh, you, gosh. Why do I give to him? They just, let's say here, crying child on a flight. Nope. Crying baby, that's what people complain about on a flight. Nope. Is there a stamp pro for a crying baby? So you can see it's pretty interesting. These are actual real tweets right here. I have like twice the amount of nip pages as one assignments. You can delete some of the extra plots. Yeah, so you want us to report the question like, can you expand upon that, Caroline? I'm trying to think what you're saying, Caroline, by that. I'm trying to think what you're saying as I just look through random tweets. Let's say here, Pepsi. No one said Pepsi. No one tweeted about Pepsi. Try here. What do you think? Soda. No one said soda? I don't know. So you can find Brian. You can find your name. Brian at the customer service deserves a raise. Nice. Thank you so much. Someone's watching Brian Williams on TV. Someone's adding their friend. So, you guys are awesome. Thank you, Vadrina. You guys are awesome. Oh, they're talking about someone else completely. But no, it's been, I'm really having, I have tons of fun. And for example, would you say the model that happens to do the best is, so is it because we're testing it on the holdout, right? The model that does the best on the holdout would be the X18, X18. Is that the answer right there, Caroline? That's the one that does the best. You know what you also probably want to do? You just probably want to take a quick scan of your matrix. And you just want to take a quick look at it and see. 15 feet by, oh, Andrew. You're cracking me up, Andrew. Like, this place is too small. I'm super excited for my new place. You guys will have to see the new studio. They'll be like, you'll have to log in and check out Stat 201. And we keep on promoting the like the Twitch channel. So we're really gonna try. I'm gonna try to have a big kickoff next semester with Twitch. So fly you down. I don't know. Things start. We are all crazy. You never know what's gonna happen. But yeah, I want to. If you guys have Twitch, use your Twitch Prime to sub to the channel, which I think we can get to once we have enough watch time and hours. I mean, you don't have to do any of this, but if you guys want, and once again, we're gonna take all the money we get from it and just put it right back to UT, right back to the students. I'm really lucky. UT treats me super well, and of course they're letting me teach from Texas. So we want to do all these cool things, like, okay, we're going to, have the studio in Texas, and I'm gonna do a lot of fun stuff. I'm gonna have a 2-camera setup. So, and I'm having my fiance help me out setting it up. So I'm super excited because I'm gonna be like, okay, she's already like helping me look for desks and stuff. I'm like, it's so exciting, everyone. I also think I'm gonna do it standing because it's all right sitting, but what's a vote? Should Brian be standing or sitting when he's teaching? Should Brian be standing or sitting? What's the vote? Should Brian sit or stand while teaching? Drive-by wedding. Oh, whatever. I don't know. Well, however Chelsea wants to get married, I'll get married. However big or small. Yeah, both. I think I think I get a little tired sometimes. That's maybe sometimes it hits me during 474. And thank you guys so much. Like sitting in a chair can be I think it's better to stand. Yeah, and so like I might get like a standing desk. Yeah, that's the thing, Brad, is when we were doing it before from the studio, I was standing and I kind of got used to that. And then I've been sitting for quite a long time now. But what I want to do is, and maybe I could do it I've just got a bunch of ideas, and I just have to get down there, start setting up the studio, and then I'm going to have a 2-camera setup. So when I hit like the second button, like it's not going to work. But I could have like a transition screen where it's like, back away from Mike there a second. I could have a transition screen where I'm like saying things or like be like, hey guys, get ready. We're about to do an assignment. Here we go. Like it would last a little bit longer. I know, right, Carly? That's what we need to do. We need like an adjustable desk, which they have those, and then you can just get like the desktop. So we might do that. And so, off your hands. I'm all right. And so I want to have like a longer transition where I'd have like maybe it'd be like a 10-second transition where it's like whiteboard problems and it has like an animation. It's like an animated Brian or something like that. But it'd give me time like to get up and walk over. So that way, like it transitions the screens. Can you help with 3? Yeah, of course. You bet. Of course. We're just chilling out. Let's do it. Let's talk about number 3. Question 3. Overfitting is one of our biggest fears when we develop a predictive analytics model. In package reg class, there's the overfitting demo. Provides an illustration that shows what happens when a model becomes overfit as it gets overly complex by adding too many variables. Run overfit demo as set up below. The EIC is a measure how close the model is to the truth. AKEK's information criteria. The model is discussed at length in BAS 320. They'll be hearing about that very soon. And it's closely related to the RMSE. So it varies. And what's funny? Brad, if you're still here, Brad should know this quite well. We just did this today as practice. Watch this right here. We're just going to make a model predicting height, with F in height, tilde weight, comma, data equals, survey 10. And now we're going to do choose order. And we're going to hope we're going to have enough room. Did we have enough room? The answer is yes. And there's AKEK's information criteria. Question 1C on 320. You got it. Argument must be fitted model null, but I've made my model. Send me your code, Connor. Send me your code. Which is funny. I was just doing this right here. Your code should look something like this, Connor. Double check with what I have written on the screen right now. And this kind of relates to 474, as you can tell. A lot of these things converge with the classes. That's why I love doing 324, back to back, because people do 324, and they're like, I got it all. Oh, is it working, Connor? I hope it's working. But send me your code if it's not working. So if you notice right here, AKEK's information criteria can be used to pick models. So AKEK's information criteria, we can kind of just find the lowest. You know what's interesting? Well, so we'd pick this one, wouldn't we? Yep, that's the lowest AKEK's information criteria. And we could use our standard, which we've practiced in class, to practice in class what we're doing. So this is what we do. We take the highest r squared adjusted, which is 0.4351,351. What do we subtract from this? Awesome. Yep. Thank you for sending the email and we'll get it done. What do I subtract from this right now with r standard in 320? What do I subtract from this right now when I'm checking the polynomial order of the model to see which one I use? I find the highest one, which I found, step 1. Step 2 is to then take what from it? Subtract. Nice job, Aaron. 100 points right there. Aaron and Connor both. We subtract that. And now we ask, does each one of these pass? Does that one pass this standard right here? Does that one pass it? Yes or no? The answer is most definitely no, that does not pass. Does this one pass the standard right here? The answer is most definitely, again, no. And what do I mean pass? I mean, is this higher than it? It's not. Does this one pass it right here? Nope, does not pass. Does this one pass? Just barely. And that's good. I mean, it means we're going to use the fourth order. So you always start with the simplest and you see which one first passes. So the answer is this. And what's interesting is Akaike's information criteria, Dr. Hiratuga, I'm probably mispronouncing his first name, but I know his last name is Akaike. He came up with this information criteria, which is about an estimate of how close our model is to the truth. The lowest it can go is negative infinity. And that's a pretty, I mean, we choose the lowest one and it kind of converges on the same answer. Now, we are not using this standard in 320. It's just another standard. But it also converges to the same answer Dr. Petrie had. And it's interesting because, yeah, so Dr. Petrie has his own way of doing it, and it's a very good way, and we have Akaike's way, and there's lots of ways to do things in stats. All models are wrong. Some are useful. So let's go to the overfitting demo right here. Let's increase the screen size. Overfit demo. Should run with nothing. Wait. Sorry. You want overfit demo as a setup below? Okay, here we go. Overfit demo. Whoop. There we go. Cool. Okay. So when it comes to this right here, for this example, what is the optimum level of complexity number of models in the predictor? Okay, cool. So what is the optimum level? Okay. So we have to look right here. When does overfitting start? When does overfitting start? When does overfitting start, and what does overfitting mean? So when does overfitting start? Overfitting is defined as what? When the model here. That's when we see overfitting starting because it's actually doing worse on new data. So when the model does worse on new data, we start to overfit because then it's learning the training too well. And so we see AIC can start to go down, but we see here that we see overfitting begin at 5, and you could say it really starts to take hold at the later values. So overfitting kind of begins at 5. I might take a peek at the graders key. So you could change the, oh, I guess it's overfitting demo, so we can't change that. Let me see what the, make sure there's no disagreement. What is the grader going to be looking at? What will the grader? And does everyone understand right here? Overfitting is when the model does not generalize well to new data. So it does not generalize well to new data. I'm trying to find. Ask questions in the chat if you got them. Yeah. Yep. Exactly what we were saying. Exactly. I just want to make sure. So there's literally the answer key kind of shown off, but just I don't want to make sure that the, the grader doesn't see anything different, because the reason I say this is sometimes there's a little bit of subjectivity to these things. And so with there being a little bit of subjectivity, who's to say someone's not like, oh yeah, so overfitting in layman's terms. So overfitting is when the model learns the training data so well that when you have it work on new data, it does way worse. So pretend the last part of this graphic does not exist. I'm going to... So pretend the last part of the data over here does not exist behind my head. Do you see how generally as the model, as we increase the number of variables in the model generally does what right here? As we increase the number of variables in the model generally does what? As we increase the number of variables in the model generally does what? So as you increase the number of variables in the model generally does what on the data it was created from? So as we increase the number of variables, this is the number of variables. As you increase the number of variables in the model generally does what on the data it was created from, the training data? No. So remember, this is RMSE. This is like relative error. So it's doing, the error is going what? As you put more variables in the model will do what on the data it was created on? The error is going down. Does that make sense? So the error goes down on the data it's created from as you add more variables. It gets better. The error goes down. So this is it getting better. And this is the data it was created from. This is the data it's learning from, the data it's trained on. Great questions right here, because this is like the theory stuff that we have to understand. So the model will do better on the data it's created from as you add more variables. So this is something I thought originally. I was like, why don't I just add a bunch of variables? Why don't I just like add every variable to it? Well, the problem is that if you add in all these variables, the model will do better on new data, but then it'll start to do worse because it overlearns the data. You see, at this point, it's doing really good, and then it starts to get worse as we had put in too many variables. It's like saying this. Imagine I'm going to learn how to play chess, which I know how to play chess, but I need to learn how to play chess better. Not that I need to, but imagine Brian wants to learn how to play chess, right? So with Brian learning how to play chess, Brian plays his brother 1,000 times. And I get to where I can like beat my brother, like consistently. But because of that, I'm going to overlearn how to play my brother in chess, and my abilities will not generalize well to new data. Now, that kind of, we did a good example yesterday with pizzas, I think it was yesterday. This goes to collecting more variables. And so we'll do the pizza example again. We'll mention that. I really like the pizza example yesterday. It worked really well. Do we still have the pizza thing up? We don't, but we can talk about it again. So let's talk about the pizza example here from yesterday, because I think this made the most sense, is you have your two friends. So let's talk about a model that would generalize well to new data. Here's your two friends, and you're going to ask them about making a pizza. What kind of model would generalize well to two different friends? If you were to ask your friends, I need advice for you, and you're going to give me 20 bits of advice or 2 bits of advice on making this pizza. I want to make this pizza to your taste. You can give me 20 bits of advice or 2 bits of advice. Yeah, it understands the original data way too well, and then it can't understand new data. So which of these, let's see what you guys say. We're going to make this pizza either with 20 bits of advice or 2 bits. Like they can say like, you should add onions to it. Like you can say, you need to tell me the 2 most important things to make the pizza or the 20 most important things to make the pizza. So which of those would generalize really well to 2 separate friends? So we have the option of, this is a good test question. We have the option of 2 bits of advice or 20 bits of advice. Which of those would generalize well to 2 completely new friends? These friends up here can give us 20 bits of advice for this pizza or 2 bits of advice. Which of those would generalize well to 2 new friends really well? Any ideas? The 2 bits of advice would generalize well, or the 20 bits of advice would generalize well? It's actually the 2 bits would generalize really well. Because imagine what 2 bits of advice they would say. They would say something like, pepperoni's good. Like, because, most people like pepperoni. Not saying it's bad if you don't like pepperoni, but like, pepperoni's good, and also extra cheese. So that's their advice. They're like, oh, you should do pepperoni and extra cheese. Now, who here is good with pepperoni extra cheese? If I'm like, we got a pepperoni extra cheese pizza, and it's from wherever you like. Like, you like Domino's, you like a Hard Knocks pizza, but it's a pepperoni and extra cheese pizza, and you'd be like, that's good. I'm happy with that. Anybody? Single person's like, I'm good with that pizza. That's with only 2 bits of advice. And that pizza would probably generalize to most people because we're not extracting South Coast. Oh, man, yes, there you go. I know Brad likes it right there. But now imagine if we collect 20 bits of advice. With 20 bits of advice, we'd have something like, okay, pepperoni, extra cheese, garlic sauce on the crust. You should make the crust crispy, And so all of a sudden now we're getting into kind of an overfit model. Can you imagine with 20 bits of advice, the model we would make for the pizza would be really, it would overlearn these people right here. So if we made the pizza, if we use the same pizza on these people, it's overlearned the people it was created from. The original data sets kind of learned the quirks of it. And then the model that's extracted too much information does not generalize well. And that's what's going on in this picture. At first, we're making kind of a not so awesome pizza. We keep getting advice and we keep doing better on the data it's created from. And we'll always do better. Well, I mean, AIC corrects for putting too many things in the model. But generally speaking, the more variables, you do better on the training, unless it has a correction for amount of variables, which AIC does. But we see right here that for the new data, we do better, and then we start to do worse. And the worst is the overfitting, because we're overlearning the training data at some point, because training will consistently usually go down. And then we overlearn the training, and we start to do worse on the new individuals. So if this was making pizzas, we should ask like 5 bits of advice. So we should do 5 bits of advice. We don't want to do like 20 bits of advice, because then we're going to make a really awesome pizza for the first 2 people, but the new people are going to be like, yeah, this pizza, it seems like you kind of catered to the taste of the people you learned from. But with 5 bits of advice, apparently we do even better on the new data. The people are like, hey, this is a great pizza, and the original people are like, yeah, it's a good pizza. Does that make sense with what's going on with these graphics? Like, these are your new people tasting the pizza, and these are the original people who tell you how to make your pizza. So this is where we test our pizza out. Why holdout is sometimes called test. This is the testing your pizza out on new people. And if you get too much advice from your original data on how to make your model will start to be overfit to the original data, and you'll start to do worse on the new data that you're trying to use the model on. Does that? So adding too many variables makes it too narrow. It makes it overlearn the original data. So the structure of the model is set to, it like memorizes, I think I've seen that in textbooks before, it memorizes the structure of the original data, and it just extracts too much information. And we would say that that's a high variance, low bias model. So over here on this end is your low bias, high variance model, and down here is your high bias, low variance. Because if you extract very little information, you'll have high bias because your model will do very badly. And if you have high bias, you'll have low variance because the model will just do consistently bad. But over here, the model has low bias because it does very well, but it has high variance because it extracts so much information. So variance is related to the size of the coefficients we're extracting, and we see that a lot in the notes, that variance is related to the size of the coefficients. And then we'll go back to number 9 right here. But does that, Vedra, does that make sense? Does that help disambiguify what's going on here? And going back to number 9, how do we decide which model is preferred when the difference in their predictive power is greater than 1? So it's RMSE. You're looking at the RMSEs, Caroline. So which one do you want? If it's RMSE, you'll use which RMSE? Great question, Caroline, for number 9. Since it's RMSE, which RMSE is the better RMSE? Which RMSE will be the better RMSE if it's RMSEs? Smaller. Yep. RMSE is typical miss. Yep. So overfitting is... Yeah, that's a good definition of overfitting. It's reverse it, other way around. Yep. Overfitting would have low bias because it's fit. Like this is the overfit right here, because you're going to do really well on your original data. It's going to have like small error on the data it's created from. And then when you use it on new data, it's going to have a very hard time. So overfitting is usually a model that has low bias. It does really well. It has very small misses. And bias is things like your RMSE. So you're going to have a very small RMSE. You'll be like, whoa, this model works amazing. Like, man, people love my pizza. Oh, just imagine. This is so true. Like, what if your friend's like, I cook the best pizza. And you're like, you do? And they're like, yeah, everyone loves my pizza. I cook the absolute best pizza. And you're like, okay, you got to make me a pizza. And they make you a pizza. And you're like, it was okay. I'm like, what do you mean? And you're like, yeah, it was okay. I'm telling you the truth. And they're like, I've been making pizza for my family my whole life. And they're 20, let's say, because I don't know. No, I'm not trying to say anything. They're like, do you get what I'm getting at here? That your friend has overlearned the structure of what their family likes. And then the way they make their pizza does not generalize well to new individuals. Does that make sense? Like they've overlearned, they've memorized what their family wants in a pizza. And then when they make a pizza for someone else, it's not kind of tailored to the new data. They've memorized, so they've overfit to their family. And so with that, they don't have a pizza that generalizes well to new data. It's overfit to the expectations of their family. So yeah, the code for one E on BAS returning won't load. There's been a loading dial for like 5 minutes now. Sylvia, I think you're running to the same thing we saw earlier. Good question in here. Probably down here on the bottom of the screen. It's probably open up your bottom menu down here, and it's probably asking you for an input. So either hit enter or hit escape. Either one of those two should get you out of that. Good question, Sylvia. A few people were, someone was stuck on that earlier, but thanks for jumping in and asking that. And Vedrina, does that make sense? I think we're good on everything. I just want pizza. I just want pizza. I swear, like, I'm going to get to Texas. I'm just going to make, my fiance's going to be like, what are we having for dinner now? I'll be like, pizza. She'll be like, we had pizza last night, but let's make pizza again. And then she'll be like, what are we having for dinner now? I'll be like, tacos. And she'll be like, we just had tacos last night. I'll be like, tacos again. Well, I mean, like, I'll be making it. I don't know. I mean, I don't know. We worked together. But, like, let's make tacos. I like tacos. I like pizza. Make hamburgers. I don't know. I just don't have, I don't do exciting things right now. I make like rice. I make like ham sandwich, or like, I don't know. Like, it's pretty boring. I'm not inspired to cook things for myself right now. I did make a taco salad thing like a week ago because I had a taco kit and I was like, I need to use this taco kit. And then I like grilled up the beef or whatever, not grilled up, just got the beef good, and then put it all into like a big Pyrex pan or whatever, Pyrex dish, and kind of layered everything. Oh man, I wish I had sour cream. Oh man, sour cream is the best. If you don't like sour cream, I'm sorry, you're missing out. But I wish I had just done layers. I did layers of cheese and stuff, like layers of cheese and chips and stuff like that, and it was really good. And that was like, was that last weekend? No, it was 2 weekends ago. Yeah, 'cause I went to see my parents last weekend. So that was like Saturday and Sunday food all day. That's the most exciting thing I've done. Any other last few questions right here? Brian's exciting time making himself his taco salad meal. It wasn't really taco salad because it didn't have any salad in it. I would have done that. Like a taco bake and then put it on top of salad and have a taco salad. I don't know. What is everyone's, let's end class with this, or let's end office hours with this. What is everyone's favorite food? What is your favorite food as we all prepare for dinner? Does anyone have a favorite food besides me? Everyone's favorite food is points. And thank you, Streamlabs, for working so well. We have to be nice to Streamlabs. Less Streamlabs now. Sushi? Sushi's good. I like sushi. Wings? I do like wings too. Like, sushi, the first time I had sushi was in a food I don't have to buy or cook. Wait a minute. Sweet potatoes. Actually, superfood. Yeah, sweet potatoes good. I got some sweet potato fries at the grocery store, like in a bag. Like, sweet potato fries is really good. Sushi. Yeah, sushi. There's Nama in downtown. Nama's got some, I think they have like, like half price sushi hour, stuff like that. Korean barbecue. Korean barbecue is really good. I think, yeah. There's like bibimbap. That's, isn't that Korean? The bulgogi, and bulgogi's Korean, right? Am I totally off on all this? I'm in Maryland. We just started phase 2. Good. Oh, well, you mean, wait, you're not saying phase 2 of unshut down thing. You're maybe saying phase 2 of fun time, happy time, COVID time. Bulgogi, yeah, and bibimbap. I can't say it. The little things they give you to start out, I've never been a huge fan of, but I do like the bowl with the stuff in it. That's really good. At the Korean restaurants, I like that. So I don't know. I try to tell everyone, just try to go out there and experience the world, because especially Knoxville, once everything gets going again, Knoxville's got a lot of really cool businesses to support. So once again, be safe, be smart, be safe. But there's a bunch of really cool places in Knoxville. There's even a place near Trader Joe's, and I can't think of the name of it. I'm trying to think, is it Korean? It's very traditional. I think it's Korean. And we had some pretty good meals there. We went there twice, and we had some really, really good meals. And it's a lot of different things I'd never tried before, and I'm always up for that. I really want to start traveling more, but we'll have the world back open up. You can do outside seating. There you go. Yep. Well, that's got it. Thank you guys for all the positivity. I will see you tomorrow morning. Please email me if you have questions. Email me if you're stuck. Remember, if you're looking at something for more than 5 or 10 minutes, email me. Just be like, hey, Brian, I'm stuck on this. I'm sending you an assignment you should send out. I'm sending you an assignment I should send out? I'll take a look at it. Oh, no. Thank you, guys. I appreciate it. It's really nice that we can do this. And, I really appreciate all the positivity and all the support this has gotten because, I've done the Zoom teaching thing, nothing against it, but I feel like this is more, from what I hear from you guys, it's like people have said this feels more like you're actually interacting with people and you're actually like in a chat, talking to people, doing things, and actually like really existing like in a class. So we're going to keep trying to improve this, and do check out the studio when we're in Texas. This isn't the end, obviously, but get ready for some really cool stuff because pretty much all of July, I'm going to be setting up that studio, and I'm really excited because I've got a bunch of tech I haven't even hooked up yet because I'm just going to be dismantling this whole thing. Like, we're going to have our last class on Wednesday or so, and then I'm trying to think if I can even really broadcast online after that because I'll be dismantling my bedroom studio because I'll be bringing it all down in my car. So that's got it. We're going to send it with the rules. Best design wins. Oh, we should check this out. Awesome, Andrew. Well, that's got it. What should we, what we should do? Jason gave us the thing. I don't know. One of these days I'll show that. Jason made an intro that we haven't used yet, and we just keep hitting with those copyright claims. I'm always afraid. Maybe one of these days. I feel like we should always show that in a special screening for people like when we do like a live event. Not that we're gonna do like live events, but like when I like am in like the classroom, I could show it and be like, this is the one no one's seen, because then it's like really cool. Like, this is not on YouTube. You have to be here to see this. So maybe next semester I might fly in and we'll have like we'll do like a business analytics society thing, and I'll talk to them, and we could have like come hang out, get pizza with business analytics society, and so we'll get to do some cool stuff. So stay tuned. Lots of cool things on the way, and thank you guys and gals for the support. But that's got it. Here we'll end with the Jason. Jason, can we keep going? Jason, can we keep going? Jason. 5 hours. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.